Hello everyone, welcome to another scientific video with temperature Productions, and today in this video we are going to discuss about the most highest possible temperature in the universe. And in last video clip you remember we discussed about the most lowest possible temperature in the universe, and in this video we are going to discuss about the highest possible temperature of the universe. So far in physics, we use the Planck's temperature as the highest possible temperature in the universe. But this is still a theoretical temperature only, not a real temperature. The value is Tp, the Planck temperature is equal to 10 to the power 32 Kelvin. 10 to the power 32 Kelvin. But actually, we have to say that this is not at all possible, and we have a separate suggestion. We have a different suggestion. And today, in this video, we are going to expose that particular idea to all of you. Planck's temperature is calculated with this equation. Tp is equal to C2 divided by lambda natural log C1 divided by lambda L to the power 5 plus 1. Actually, I am not going to give a huge detail about this particular equation because we have enough sources in the internet and in books to find out details about this particular equation and how to calculate the Planck temperature. Tp is equal to 10 to the power 32, 10 to the power 32 Kelvin. Not possible in the real universe at all. Actually, this is not possible in the real universe at all. And in this video, we are going to explain why is that so. We have a different suggestion. Using the molecule and particle movements. We can calculate another temperature as the highest temperature of the universe. And today, let's see that. What is a temperature? First of all, to understand, to find out, to calculate the highest temperature of the universe, first of all, we have to understand what is the temperature. In the last video also, we discussed about this one. Temperature is an indication of the thermal energy that any object has. Thermal energy in the object is not existing as thermal energy, it exists as a form of kinetic energy, as particle vibrations. So every particle is vibrating at any temperature to show that how many of thermal energy is there in those particles. Means if there are high amount of thermal energy, the particles of the object are vibrating fast with high speeds and with high magnitudes. That is called a high temperature. When the temperature is low and the thermal energy is low in the object, the particles are vibrating slowly with low magnitude, and we call it a low temperature. How to prove this one? In last video also we discussed about that. Take a hot sample, put some pigments and heat it up. As you heat up, you can see those pigments are vibrating faster and faster. As you decrease the temperature, you can see those particles are vibrating slower and slower. Same as those pigments, the water molecules are doing the same. At high temperatures, they are oscillating fast, they are vibrating fast with high magnitudes. In low temperatures, they are vibrating slowly with low magnitudes. So these things are happening, and that defines how much of thermal energy is there in the object, and also how much of temperature is there in the object. What is the temperature of the object? So at high temperatures, the vibrations are high, faster with high magnitudes. Okay, now we are going to calculate another set of temperatures as the highest temperature of the universe. As I know, to the best of my knowledge, so far in this world, no one has calculated this temperature. So I have to name it. I don't have another name. I don't have separate name. So I'm going to name those temperatures using the name of our YouTube channel, Temperature Productions, and I am going to name them for the moment, only for this moment, temporarily. I'm going to name those temperatures as temperature points. Okay, now let's see how to calculate those temperature points. First of all, we are taking the equation of the absolute gas equation. PV equals nRT. P is the pressure, V is the volume, N is the number of moles, R is the universal gas constant, and T is the absolute temperature. Then we are taking the PV equals 1 by 3 mNc bar square equation. Here P is the pressure, V is the volume, 1 by 3 is a constant, M is the mole mass, N is number of moles, and C bar square means the mean average speeds, square mean average speed. Okay, now we can make a calculation like this. PV equals P. Here PV equals nRT. Here PV equals 1 by 3 MNC bar square. So nRT is equal to 1 by 3 MNC bar square. So number of moles and number of moles will be cancelled out. Number of moles and number of moles will be cancelled out. So RT is equal to 1 divided by 3 mole mass C bar square. So T is the absolute temperature. So T is equal to M C bar square divided by 3 RT. Absolute temperature is equal to mole mass. This is the mean square particle vibration velocity or the speed divided by 3 RT. Now, as we know, in the universe, the maximum speed or the maximum velocity that a particle can achieve is the speed of light. In the universe, there's no other velocity existing greater than the speed of light or the velocity of the light or the speed of light, whatever. So, speed of light or the velocity of light is the highest velocity or speed that we can obtain in the universe. So, if the particles are vibrating with a certain speed, that particular speed has the highest velocity, the highest amount, highest magnitude, or the highest speed is the speed of light. So now we are going to substitute C bar, C square bar instead of C square. C is the standard notification for the speed of light in physics. So C square means the speed of light square. So in here we are assuming that the highest possible velocity or the speed that a moving particle can take is the speed of light. So we are going to substitute that particular idea in the equation. And finally we can take an equation like this. T equals mc square divided by 3RT. And using this equation we are going to calculate all those temperature points. And there are plenty of temperatures because M for hydrogen the molar mass is 2. For oxygen, the molar mass is 16. For nitrogen, for oxygen, the molar mass is 32. For nitrogen, the molar mass is 28. But if we take a heavy element like thorium, the molar mass is 232. So even at high temperatures, the thorium can also behave as a gas. So we can put that value also here to calculate that points. And in the next clip, we are going to calculate all those things, and let's move on. Okay, now we are going to calculate some temperature points. So the highest temperature of the universe temperature points for H2. For hydrogen gas, first we are going to calculate the temperature point for hydrogen gas, and the molar mass of hydrogen gas is 2 to the power 10 to the power minus 3 kilograms, and speed of light is 3 multiplied by 10 to the power 8 meters per second. Divided by 3 is 3, R is 8.314. So finally calculate this part, we can take the solution as 7.217321571 multiplied by 10 to the power 12 Kelvin. Okay, now temperature point for oxygen or O2. So O2, the molar mass is 32 multiplied by 10 to the power minus 3 kilograms per mole. So the speed of light is same, 3 multiplied by 10 to the power 8 square. 3 is 3, R is 8.314. So finally, the temperature point for oxygen or O2 is coming as 1.154678855 multiplied by 10 to the power 40 Kelvin. So in the same way, we can calculate another value, temperature point for helium. So after calculating this part, temperature point for helium comes 1.4436464314 multiplied by 10 to the power 14 Kelvin. And if these are all very high temperatures. So in these high temperatures, Even heavy metals like thorium can behave as a gas. First it will become liquid, then it will become gas. So at the gaseous state, if thorium is behaving as gas, then we can calculate another Tapos point for thorium as well. And today now, in this part, at this moment, we are going to calculate a Tapos point for thorium as well. So Tapos point for thorium is in the same way, the thorium molar mass is 232 multiplied by 10 to the power minus 3 kilograms per mole. So once applying that particular value here, we can calculate the value for thorium also. That was point is 8.372093 10 to the power 40 Kelvin. So that's the Tapos point for thorium. But we have a problem. At these high temperatures, will the atoms or will the molecules behave as atoms or molecules? As we assume, the atoms and molecules will be disintegrated at these high temperatures. So after disintegration, there will be only subatomic particles. So now we are going to calculate another Tapos point for subatomic particle. The smallest subatomic particle that we can use to calculate a temperature is the electron. So electron, Tapos point for electron. So the molar mass for electron is 1 divided by 1840 multiplied by 10 to the power minus 3 kilograms per mole. Kilograms per mole. Kilograms per mole. So once we are applying this particular value into here in this place, what will happen? The value will come, the Tapos point for electron